Okay, hi everybody. Well, I can see that you hear me. My name is Lior. I'm from Adobe Firefly, which is our GenAI organization. Now, this talk was supposed to be given at first by Ursin Umer, who leads our platform part of Firefly. He's a lot more, platform biased than me. I'm a machine learning person. I come from research. And it's actually interesting. A very similar set of slides. These were his slides originally. And he presented them at GTC. And he really focused on the nuts and bolts and scaling up in the platform. And I kind of hijacked them and talk a lot more about weird video bugs and how do we scale video model and for what purposes. So if you're interested in looking at the recording of the GTC talk, I think he probably took it in a very different direction than what I am. So like I said, Firefly is the Adobe GenAI organization. We started with an image model. And then last October, we put out our first video model. And that's what my team does. I build a foundation model on top of which we build all the video applications. And we collaborate with our website, Firefly, where we ship our models, and also from other companies, and with our first-party platform, like flagship products, like Premiere Pro and Photoshop. OK. So today I'm going to talk about how we built the Firefly video model, the different considerations we had when we decided on the architecture, on the data that we're going to use, on the training regime. And then when we went into training, our data strategy, which I think differentiates Adobe from other companies, the curriculum for how we train the video model. And this is an evolving journey. We trained several versions of the first video model, and now we're working on the second video model, which I can't talk too much about, and some key insights for the scale and efficiency for training. And then I'm going to talk a bit about inference and how we deploy them. And this was really more Ursin's forte, but I'll try to do my best on that part. OK, so let's start by talking about the model itself. Such a 1950s clicker. So when we started thinking about, and when we think about what we want to train the model, we take into consideration several kind of size aspects. One is what is the data set size versus what is the model size. We try to fix some constraints, like what is the compute that we have, how many flops we want to invest, down the stream, like when we run inference, how expensive do we want it to be, and build a plan. So we look at the data available to us, how much we can acquire, which is a bit of a long-term proposition, and then the compute budget. That's been a headache for me, I gotta say. Adobe is not the richest company in the world. I think the big behemoths, OpenAI and Google and Meta, they have an order of magnitude more GPUs than us. But I think that puts us more in common camp with most companies, where GPU and budget for that is always a real consideration. And finally, like I said, we think about the quality versus the efficiency trade-off. Do we want to generate at 1080p? It means we're going to have to generate at such high resolution. The sequences are very long. It's going to be very expensive. Do our clients actually need it? OK. So regarding architecture, this again is this very interleaved concept. How do we choose a model? We have to think about the characteristics. And when we started training for video, we already had existing models for image. So we already had a pretty good image database, and we started collecting video data. But we knew that we still wanted to start pre-training with images. And I'll talk about it in a few minutes, but in our training, we go from images to images and keyframes, and then add like short videos and slowly grow, both in the length of the videos and in the resolution, aspect ratios, et cetera. We considered the scalability and stability of the architecture that we're going to use. I'm going to give you a sneak preview. We chose diffusion transformers like everyone in the world. I'll go into that in a bit. And finally, when we think about the architecture and the training process, we also think down the line about inference time, about deployment. What types of controls do we want to put? I think this is another thing that we want to differentiate in our products. Adobe's customers are creatives. They require a lot of pixel-perfect control. They have artistic vision. Right? It's less casual users who just want to put in a prompt and get a result. They know exactly what they want to get. So that was really important to us, to support a pipeline where they could ideate and where they would have strong controls over the output. And this affected everything from the choice of the VAE to see how well we support fine-tuning versus adapters, for example. OK. So what did we choose? So first of all, like everyone else in the world, we chose diffusion transformers since they allow us, they're a simple architecture with full attention, feed a lot of data into it over a lot of GPUs, and the model will be able to soak it up. VAE turned out to be something we spent quite a lot of time on. We trained multiple versions of our VAE with an encoder-decoder. We wanted improved conditioning and alignment. We wanted to be able to represent high resolution and have good motion. And we wanted, and realistic motion dynamics. What ended happening is that we also grew very proficient in replacing VAEs on the fly. And that also affected our training, because in the beginning we had a pretty decent VAE with decent PSNR, but as we started to train, it was not high enough compression. So the sequences were long, so we switched it with a higher compression VAE. That introduced problems where we started seeing artifacts in the generation quality, and also the encoding and decoding times were more prohibitive. So we solved that in a few different ways. We had minor iterations over the VAE, kind of improving the PSNR over time. We rewrote our encoders and decoders to be a lot more efficient so we could actually deploy them. And we also applied some other tricks to the architecture, which if we have time, maybe I'll get to it in the end if you guys are interested, to just be able to deal with such long sequences, like 100K tokens and above. Cool. Knowing what features we want to support down the line, we wanted to support info. This is also pretty vanilla, right? For text prompts, for images, for reference images, and to do image to video. And today we allow a custom keyframe generation. So you can give the first frame, the last frame, or several frames in between. And also video input to do video to video transformations, which can be everything from stylizing an existing video to extending a video, which is a feature that we shipped in Premiere Pro called GenExtend. So I put here a couple of examples. The top example is output from our GenExtend algorithm, which is shipped already on Premiere Pro. This allows a creator, a video editor, on the timeline, take a video and just drag it and use GenAI to extend it to 2 seconds. This was interesting and a very different use case than text to video and image to video because it is the opposite of creative, right? You want to stay really aligned to what the video is already showing. Like if the ice cream is moving one way, right? If the people in the boat are rowing, right? People are talking, it has to be very seamless. This is used a lot when people have B-roll, not quite enough, and they want to extend it maybe to match the beat of the video, right? Second, when we work with Premiere Pro, our partners, they had a lot of technical demands that you don't really see from text to video. Like they wanted us immediately to go to 4K. They wanted not just 24 FPS or 30 FPS, they wanted 60. They wanted HDR. They wanted a lot of things. And we accommodated them, and it kind of drove our development. But on the other hand, we knew that we still wanted to ship text and image to video with other features, where there, it's a lot more creative. In the end, we ended up doing joint pre-training and what we call mid-training, but then we did different fine-tuning and post-training for GenExtend, basically, like I said, teaching the model to be boring. Okay, so jumping into training. I'm notoriously bad at keeping time, so apologies if I won't be able to get through everything. First thing about training, responsible data strategy. Like I said, it's something that differentiates us. We have, it sounds very vegan, we have ethically sourced data. What we started with Adobe stock, which has really strict moderation, on violence and nudity and safety, right? And model releases for all the people appearing. And that gave us a really good solid basis. On top of that, right now we do missions where we commission videos from different production houses, and we also acquire content, but always with an eye to make sure that we have the full rights to train on it, not infringing an artist's rights. I mean, these are our customers. We want to enable them and not replace them in any way, of course. So this results in commercially safe models. We can have a long philosophical discussion if that's the right decision, but it's one of the constraints that we have that makes my life interesting to deal with. The curriculum, like I kind of said before, we do go from small to big. We start by preconditioning the model to understand images. understand spatial relationship, understand different subjects, and start getting that text-to-image alignment. We continue with low-resolution videos where I think there's a lot of this in text. But it starts to learn the dynamics and the motion and the temporal part of the video. And when we started going to longer sequences, to higher resolution videos and longer videos, the sequence length grows. With full attention, the latency grows quadratically, which is a huge problem for us. So most of our training is done on lower and kind of medium resolution videos. And only in the last push, when we're pushing towards an actual shipping goal, we know we need to ship a version of text-to-video or GenXN, then we take it to the last level and really learn high resolution. Okay, well, I said this. Good for me. We're making progress. Okay. This is a very Urson slide. So when the video resolution increases, the tokens increase, right? I mean, it's very easy to deal with 10K tokens, 20K tokens, but when it gets to 50K, it becomes really hard to manage. And that's where having a really strong platform team and support becomes really important. We worked with them, the modeling team, worked with the platform team kind of hand in hand. Because really the 10% of iteration that we do at the highest video scale take over 90% of the total training flops for our models. So what we need to do is we need to make sure that we utilize them properly and we integrate all the tech we need, like parallelization, like sharding, to keep our GPUs at optimal efficiency. I heard, by the way, something that was mentioned in the previous talk about data loaders. That became a huge issue for us, because we had our GPUs that were training, but for VAE, we couldn't really pre-compute because we kept switching the VAE with better and better versions. So we had 2 lines of data servers. One was data loaders loading the MP4, kind of massaging them according to the data set, kind of aligning them with a prompt, with T5, scaling them to the size required and to aspect ratio required. But we also computed the VAE on the fly. So we had a second line of what we called we still have them, just-in-time servers, which take a copy of the video, calculate the latent representation for training, and also when we train GenXN and we actually have an input video. In addition, like I mentioned, we collaborated with our platform team to do full sharding and then hybrid sharding, and we moved to really massively parallel sequence parallelism in our current training. And by the way, all the videos that are kind of running at the side of these slides are all from the Firefly video model. Okay. Not sure if this is data setup, but one thing that we want to do is we always want to optimize and keep optimizing as we train the model. Our goal is to get to FP8 training because it's much more efficient. We started BF16 and moved progressively once it was stable. We found out that if we started with FP16, we got divergence pretty fast, didn't get good results. So we started with BF16, moved to FP8, and also our platform supports very close monitoring. So when our model diverges, or when we have any errors in any of the GPUs, we get really fast alerts and are able to restart the whole process from the less stable checkpoint. Here's something that is close to my heart. And I talk a bit about it in the takeaways, but you find the weirdest bugs when you train these media generation models. I really feel like we've invented this new computing paradigm with generative AI and LLMs, and we don't quite have the tools yet to know how to deal with them. So kind of a sampling of bugs that we had to fix during it. One of them, we called it the Confetti bug. Almost every prompt that we generated, and this was 6 months ago, all of it generated these very kind of high-frequency artifacts that had nothing to do with the prompt, like confetti around the peacock or like dollar bills floating around the man's face. And that perplexed us. And there was like a few sleepless nights. We eventually tracked it down to like a literal bug in the training loop. Something with our flow. I won't bore you with the details, but that was marvelous. Our VP was actually the first one to discover this because a bunch of us thought it was cool. But he said, cool, but not really aligning with the prompt. That is another thing, right? I mean, how do we even evaluate these models? It is so subjective. Today, we use VBench 2, which is pretty good for kind of objective things. And we use human raters, which are expensive and slow, but do the job. But I really think this area is in its infancy as regards to evaluation. Let's talk about a few more cool bugs. Dancing has been something that has been really hard for us to nail. This is actually one of our better dancing results, and it's after post-training with highly curated data. And still, it doesn't feel quite right. Another recent bug is our people stopped blinking. She blinks like once, and this happens a lot. Like people just sit there unnervingly not blinking. And finally, and this is really recent, whenever you try to specify an expression in the prompt, there's no subtle expressions anymore. Everything is just really mad, or really happy, or really sad. Again, makes my job exciting, but I was just chatting with someone I know outside, and I was telling them that I don't like diffusion because diffusion is so, diffuse. The loss has no meaning. It doesn't relate to video. There's no real way for us to explicitly say what type of emotions we want. We can kind of implicitly affect it through our selection of data and post-training. And there have been really interesting works like inference-time or fine-tuning, I don't know, Video Jam comes to mind. But nothing really large scale, and that's my gripe with diffusion. Okay, moving on to inference, again, really quickly. But having the model in hand is not the last step. Right now, we need to actually turn the model into a feature. And usually, the model does not live by itself. We have this whole pipeline where we have a text prompt coming in from the user, potentially with an image, if it's image to video. We have to do prompt understanding, to do debiasing, to do safety. The prompt can really transform at this point. So we try to do evaluation with vanilla prompts, but also with rewritten prompts like this. Then we feed it into image encoders or video encoders if it's V2V, run it through the DAT blocks and the decoders, and then run it through safety again. Because you could potentially have a very innocuous prompt and maybe an innocuous image coming as input, but still the output video will combine concepts in a way that is not acceptable, right? Like you could put an image of a child, and then your prompt could be like smoking a cigarette. We got to figure out that in the concept of the child and the cigarette, probably this is not the output that we want to get. And we do try to be really, responsible. Okay. So there's a CPU pipeline that orchestrates this ML pipeline, and we have a very complex system out there with our deployed models. We have multiple endpoints. I think I kept the slide for that in. Okay, sorry, I'll say this first. Sorry, I inherited some of these slides from Urson, like I said. So some key insights for the scale and efficiency. The DAT block is the most intensive part of our inference pipeline. If we run it unoptimized, this is a bit old information, 40 steps would take over 2 minutes to generate a short video. I think Urson's number were based on our previous model, 540p videos for 5 seconds. Now we generate at 1080p native. We can generate 5 seconds or even a bit more, and it can go way, way over 2 minutes. So obviously, we can't ship like this, right? This doesn't really allow ideation. So we do multiple layers of optimization. We do TRT runtime with optimized kernels, which gave us 30%. We add mixed precision at inference time to get another 70%. We do CFG distillation at the bare minimum to get another between 30 and 50% improvements. And we also we utilize distillation. This was done so far more for the image model, but we've been using DMD and also recently MMD to optimize our models for the image pipeline, and we're doing it now for video. In general, we have multiple models deployed in inference, and load balancing and keeping it at scale is really critical for us. So we have a global queue of requests coming in from the Firefly website, as well as from our clients from Photoshop, Premiere, Lightroom, all of which have AI features deployed. So these multiple pipelines with multiple models all work on a custom autoscaler, which takes a look at demand. It gets updated every few minutes and dynamically loads the models depending on the demand at that time. And it fluctuates with time of day, time of week. And obviously, when we launch a new feature, there's always a spike in usage of that. OK. I'm almost good at time. I think I ran out of time. But here are my takeaways. Hopefully, if you remember something, you'll remember this. Training foundation models takes a big team, a lot of skill, and also a strong sense of purpose. And I think maybe I need to explain the last part of it. It's extremely expensive. It really requires a lot of effort. That's always up the hill because there's always another big company putting out an amazing model, right? Google came out with Veo 3 recently, mad props, amazing model. They immediately put audio-video integration on top of my list, so made my life a bit harder. But I'm excited because it drives the whole team forward. But that means I need to keep convincing my leadership that we need to continue investing in foundation models, kind of be at the forefront of video and image, right, all modalities. Second, I kind of whooshed by the fact that we use diffusion transformers, and that's because I think that the good architecture improvements propagate really fast through open source models and through papers coming out. So you gotta focus on what differentiates you. Having unique data at scale, having tight controls, and having a capable platform that is able to support training foundation models and turning them into features is a big key. As I said earlier, this is my kind of pet peeve. We don't really have any debugging or evaluation tools for this new paradigm of media generation and AI that we have created. And finally, video is really cool. Before I was working at Adobe, I was working at Meta and GenAI, and before that I was in computational photography. But I don't know, things just keep getting cooler every year. So with that, I conclude. Video rules. Thank you.